Hi, my name is Letícia Deck. I'm here to present the paper Real-Time Anomaly Detection in Data Centers for Log-Based Predictive Maintenance using the Evolving Fuzzy Rule-Based Approach. The main objective of this paper is to provide a solution to online log-based anomaly detection problem in a non-stationary scenarios using the granular computing-based method, the Evolving Gaussian Fuzzy Classifier. The background scenario are the computer centers of the worldwide LHC computer grid. It's the network infrastructure that supports the physics experiments at the CERN, the biggest particle accelerator in the world. In especially, we use the log data from the WLCG Tier 1 at the Italian Institute of Nuclear Physics at Bologna. The development of the predictive maintenance solutions are important because of the high luminosity LHC project that will hugely increase the amount of experiments and data analysis, increasing the complexity of the system. Consequently, it will be increasing also the amount of the log data generated to keep the quality of the service of the whole infrastructure. So the core of this project is the anomaly detection problem. To solve it, we suppose that the amount of the event occurrences at the system is proportional to the rate of log production. This metric is named login activity. Here I present a solution, scheme in 3 blocks. Here, the first block received the online data stream, extract the login activities, transform the data distribution to a Gaussian, and extract from it 5 statistic vector through a sliding windows strategy. This structured input data is tagged using a control chart strategy. At the end, we have a structured data pair that is used at AGFC, the classifier, to making an incremental supervised learning. And at the end, we have the estimated class of the online stream. Here is the second block, the control chart with label. Since after the pre-processing, the data stream is given by a Gaussian, we can use a control chart to tag the samples. The control chart is a chart used to monitor a process based on the central limit theorem. Based on that, we can say that 67% of the data are in the green bands, 28% in the yellow bands, and 4.7% in the orange bands, and 0.3% in the red bands. So in this way, we have 4 different classes: the normal system condition, low severity, medium severity, and high severity anomalies. This is a 4-class classification problem. And to generate this wiki tag, we use just one of the 5 statistics extracted from the data, the mean of the login activities. Here we have the third block, the Evolving Gaussian Fuzzy Classifier. This method is based on the granular computing paradigm, in which the input sample is associated to information granule. And this granule is associated to a class. Each class to exist have at least one granule, and the granule is composed by the unidimensional Gaussian sets in the product of Cartesian space given by this rule. This is the rule I associated to the granule I. AI is the Gaussian, X is the input vector, and N is equal 5. The method received the pair input and a vector and the weak label and give the estimation class. The method received 2 hyperparameters: the granularity that give the plasticity of the granule, that represent how much the granule can adapt itself to incorporate new data, and the evolving HR. That is how much rounds I would like to remember about the inactive granules. Here we have the learning algorithm of AGFC. the 5-column input vectors is initially tested. If the composition mean of the activation levels are bigger than the granularity for all the granules, so I don't have an candidates to absorb the new data, and I have to create a new data. This is because there is no rule that was activated enough to absorb this new data. Otherwise, the most active candidate is updated and return his associated class. After all of this, I update the granularity, and if needed, update also the set of rules. Here we have the result of experiments. This table summarizes the results of averaged over 5 shuffled data sets extracted from the log records. I have 4 different data sets constructed with the same data log using different size of sliding windows to extract the 5 columns vector stream. As we can see, increasing the window, the size of the windows, we have the increasing of the accuracy of the method. And this is because the slide windows work as a low-pass filter, filtering the stochastic component of the log stream. And here we have the best result of a 92.5% of accuracy to the 60 minutes windows using a compact set rules of 30 rules. It's important to see that the rule sets all the rule sets are compact, and it's important to avoid overfitting, since at the limit the rule sets can have the same size of the amount of the samples given to it. Here we have a snapshot view of the granule sets. And this can represent system status at the moment. And each Gaussian here is a granule, and each granule is associated to one of the possible classes. Here we have the topological view, and we can see better the granule distributions in the feature spaces of the previous slide. Just remembering, the red is the normal, the yellow is the low, the orange is the medium, and the red is the high anomalies. You can see the overlapping of the granules in the feature space, but the overlapping occurs mostly in the neighboring of the classes. That is, high with median, median with low, and low with normal. And this highlights the power of the method, because it gives a nonlinear frontiers among the classes, and provide misclassification in the light case. Here we have the confusion matrix. Just to illustrate the previous results, we have an example. And here we have the AGFC class, that is estimation class, the weak target class, that is a target class. This is the possible classes. And if you take the worst scenario here, disease is about the high severity anomaly, and the misclassification is concentrating the medium severity anomaly, that is in the neighborhood of the true class. So if you take any rows or columns, you will see that this pattern remain. If you are working with anomaly detection, we are worrying about the anomaly data. And if I take all the anomaly data to be processed, we have 33% of the original log data. And if I take the 2 highest anomalies, we have 5%, and the highest at 0.3% of the original data. So to conclude this work, we provide a general proposal solution to the log-based anomaly detection problem in a non-stationary and stochastic scenarios. Our best results was a 92.5% of accuracy using a 60-minute slide windows, and with a compactness rule set of 14 granules. This strategy gives a process and priority scheme to the log-based predictive maintenance systems, reducing the amount of required processing data to 33% in the worst case, being a base of feature extraction and selection. And to finish, we have here the track reference. The first is this paper, and the second is the AGFC paper. Thanks for watching.